Hello, and thank you so much for joining us today. We are excited to share our first webinar installment of 2020. We are going to be discussing 2D and 3D motion analysis today. And as you can see with the title of the presentation, 2D versus 3D, what's right for me? We will also be producing several more webinars this year, so please stay in touch and keep your eye out for upcoming events. A couple other housekeeping items. For any questions, please type them into the Q&A section, and we will do our best to answer as many of them in real time, during the question and answer section of the presentation. Otherwise, we'll certainly take copies and be sure to get in touch with any folks for any questions that we are unable to answer during the presentation. My name is Zach Scarano. I am the Director of Product Management for Noraxon. I have been working in the industry for about 6 years, and considering Noraxon's multi-device platform, I've had the privilege of gaining a unique understanding of the different tools available for human motion analysis. I hope to share some of that understanding with you all today so that you can make a more informed decision about what technology is best for your needs. Our first goal for today's webinar will be to define 2D and 3D motion analysis, as well as identify some of the technology options available on the market. Next, we will discuss the advantages and disadvantages of both technology types. We'll take a quick look into the research and see what some of the peer-reviewed literature has to say. We'll finish up with a short side-by-side review of the two modalities to see how they stack up in the real world. And finally, we will have some time for questions. Again, please feel free to type your questions into the Q&A section during the presentation, and we will do our best to address them all before wrapping up today. Let's begin by defining the anchor of our discussion today. Human motion analysis is the method by which human movement is measured. It can be traced all the way back to the late 19th century from the pioneering work of Edward Muybridge, who first developed techniques to capture the image sequences of equine gait. Perhaps some of you have seen these videos before demonstrating multiple grayscale images of a horse trotting along. Of course, motion analysis has since evolved substantially in parallel with a lot of technological advancements, as well as the increasing demand for faster, more sophisticated techniques to capture movement in a wide range of settings, going from clinical gait assessment to sports analysis and even into video game and movie animation. Certainly, one of the most popular applications of human motion analysis is gait assessments. Gait analysis is performed on a routine basis by clinicians all around the world, and also makes up a significant portion of the biomechanics research that we see. The most common method for gathering gait analysis data is simply doing observational gait analysis, visualizing, seeing with your eyes how somebody is walking and understanding their movement patterns. Of course, that takes a certain expert, right? However, nowadays, the demand for evidence-based practice is ever increasing. And since observational gait analysis is a relatively subjective method for analyzing, it tends to conflict with the demand for validated results. Enhancing observational gait analysis with several measurement modalities is typically something that some of these clinics or research labs are doing, for which motion capture is usually the center point. Using motion capture and other technologies like EMG or force plates provides a greater understanding of the performance determining aspects of the technique, helps identify injury risk factors, and can also facilitate recovery from injury or trauma. Now, regarding the use of motion capture, there are generally two measurement principles that are utilized: two-dimensional analysis and three-dimensional analysis. For a 2D system, the data is measured in two planes. And what I mean by data is, first, we have 2D coordinates, which provide us access to looking at information in side to side, as well as up and down within the frame of the video. And then, of course, we have pictures and videos, which arguably are the most valuable forms of data gathered from a two-dimensional motion capture system. Generally, the two planes that these are measured in are going to be, first, the sagittal plane, looking at things like hip flexion, knee flexion, and then also the frontal plane, understanding anatomical data such as hip abduction. Essentially, this means that you can understand how somebody is moving, but it's a flat image, so to speak. You're only seeing one portion, and as we all know, the human body moves in 3 dimensions. We are a 3-dimensional being, and we also experience additional aspects to our movement outside of this side to side and up and down coordinates. So with that, we can employ the use of a 3-dimensional system to capture motion. And 3D systems will use modeling to represent the motion in 3 planes. The data for these systems are seen as position or coordinates within a certain known volume. And then also orientation. How are certain anatomical landmarks or rigid bodies oriented in space? And this is what makes a 3-dimensional system significantly different than a 2D system, because we can add depth. We are no longer limited to just one plane of information. And as we can see here in this graphical representation, you can see that there's depth provided. We have a z-axis. We're allowed to understand rotational components, whereas before we were confined to just the 2 dimensions looking up and down and side to side. Using this information, we can model the skeletal system. So we can look at the depths and the rotations of the human body during movement. And just the same as a 2D system, we're capturing data in the sagittal and frontal planes. But then we also add in the axial plane or the transverse plane. And the depth that we receive from a three-dimensional system allows us to assess and evaluate information within that plane. So, what are the options? Of course, there's plenty of technology out there to be utilized for various measurement reasons. We have two-dimensional video, which of course, as we described, the most valuable information that we can grab is the video itself. Being able to slow down the video and see the distinct movements or the details of the movements can enhance your observational gait analysis just from the start. Our eyes are only able to capture so much information within a given amount of time. So using simple 2D video and being able to slow that information down allows us to see much more than we would otherwise in a normal real-time scenario. Of course, there are those experts out there that can look at somebody walking and apply, subjective analysis, but very, very highly accurate subjective analysis. They're trained individuals, people such as Irene Davis or Chris Powers or many other internationally known therapists and researchers that have looked into this information for decades. Another option would be utilizing wearables or three-dimensional inertial systems. These systems are emerging, a technology that has been developed and practiced for probably the last, 10 to 20 years. So not as much time that has been put into it as some of these other modalities, but certainly one that allows for some interesting aspects to be utilized, particularly the idea that you can be portable. You don't have to be within a certain frame of a video or another camera to capture this information. And we'll discuss the advantages and drawbacks of each of these in here in just a moment. Our next option, and what is often dubbed the gold standard within motion capture, are 3D optoelectronic systems. So these are typically marker-based systems. They either utilize passive or active marker sets, as well as multiple cameras positioned around a known volume of space. And they're visualizing those markers moving through that space. With the information gathered from capturing those markers moving through that volume, the kinematics or the anatomical angles can be derived from those different positions of those markers over time. Next, we have another form of another emerging technology, which would be a three-dimensional markerless system. These are typically focused or centered around some sort of machine or computer learning algorithms where they're taking multiple images, so still utilizing video, still utilizing cameras, but then taking those images and processing them to create these anatomical models so that you can register three-dimensional components. Now, if we go back and we look at some of the limitations and advantages of each of these, we can review and see, okay, where do certain aspects fit? So of course, if we look to two-dimensional video, as we've discussed already, these are going to be mostly valuable because you're able to see what's going on in reality. You have full evidence of the individual moving, and there's no question that it's that person. That is always going to be useful. There's no way around that. Of course, the limitations, as we'll get into here, is that you're limited to these two dimensions. And given that the human body moves in three-dimensional space and rotates, we're missing out on a whole piece of information that could potentially lead to some sort of discovery or opportunity to create a fix or affect change for an individual who may be suffering from pain or a certain level of impairment while they're walking and or running and performing other activities for that matter. 3D inertial systems, typically operating with wearable wireless sensors positioned on various body segments, offer several advantages. You have the ability to be completely unobtrusive and free of movement while capturing this three-dimensional data. As I mentioned previously, this also offers you the ability to be fully portable, move into spaces that are maybe more realistic, take out some of the effects that you might see from an individual walking on a treadmill and actually have them walk down a hall. Some disadvantages, however, include some susceptibility to environmental effects. The 3D inertial systems tend to operate with a magnetometer which registers where magnetic north is and uses that as one of its inputs to provide that orientation that we had discussed earlier as part of the data set needed for a three-dimensional system. Of course, companies and researchers alike are looking into how to manage these environmental effects with wearable systems. And I can tell you from firsthand experience that almost daily we are making strides in the right direction. But what's been great to see, especially over this last decade or so, is the increased interest in using these wearable systems as an alternative to some of the, more gold standard or, historically validated systems. As the technology enhances, becomes smaller, faster, lighter, and the algorithms for handling that information improve as well, it's only a matter of time before those systems can essentially be interchangeable. Now, of course, this brings me to our, again, quote unquote, gold standard, the three-dimensional optoelectronic systems. These are systems that have been utilized for decades and validated among several research articles. This is going to be your standard system that you would see built within a traditional motion capture lab. Again, typically the center point for any sort of movement analysis that might occur, alongside the utility of an EMG system and perhaps force plates to understand the kinetic and neuromuscular activation patterns during movement as well. So while these systems have been demonstrated to show the highest level of accuracies and are arguably the most trusted motion capture systems on the market, they also come with their drawbacks. Generally, they're going to be on the more expensive side, and they also have a certain set space requirement. So you need a dedicated room to be able to operate one of these systems. And typically that's also going to have to come into play with having a clean backdrop, if you will. So an environment that is conducive to capturing these marker sets as they're being moved through this space that's set up. In addition to that, some of the drawbacks are also that the learning curve is rather high. So being typically takes a dedicated individual to operate one of these systems with, you know, maybe years of experience of using this type of information in order to really use this equipment to its full potential. And finally, we'll bring up the emerging technologies with markerless motion capture. The idea behind this is actually a bit older, but we're seeing more and more commercialized systems appear that provide markerless motion capture. These can be anything from, you know, more of the research level systems to even some systems that are being utilized in clinical spaces thanks to some of the camera technology that's been developed by Microsoft and other major corporations. The most interesting thing about these systems is that it does not require touching the subject. You do not have to place sensors on them. You do not have to place markers on them. They simply enter into the space that you have set up. And the idea is that with some image processing and machine learning, you can calculate these joint centers and determine that anatomical data. Sounds great, for sure. The drawbacks here are going to be, again, that you're still taking two-dimensional pictures. And even though they're compiled to create this three-dimensional model, it can often be made inaccurate by certain movements, and there can be difficulties for capturing some of the information in that third dimension, that transverse plane. Of course, that's why we move into a 3D system in the first place. You want to see that rotational component. So there's these emerging technologies and some of these that are more standardized. And the idea here is to be able to present them to you so that you can have a better understanding of what makes the most sense. Considering that Noraxon has options for two-dimensional video and 3D inertial sensing, I'm going to continue to focus on those as we move into our examples later on in this presentation. But regardless, the benefits and the limitations that we discuss overall are going to apply to all four of these modalities. So let's talk about some of the benefits here. First, we'll discuss two-dimensional. So 2D video systems, they're typically more economical setups. They tend to not come with a high price tag, so they can usually be purchased and operated within most spaces. In fact, most people have a 2D video system in their pocket right now, and a pretty substantial one at that, given the camera technology built into many of our smartphones. Aside from that, 2D systems tend to be quicker to set up. Usually, if you're only capturing with one camera, It's just a matter of positioning that camera in the right area to capture the data that you need. Otherwise, maybe it's 2 cameras to get that second plane of motion. There's usually a moderate learning curve that's applied to these two-dimensional systems. Again, capturing video is something that we're all mostly familiar with. And then some of the systems that utilize marker tracking or drawing on the videos are generally intuitive operations that with a little bit of practice can be mastered fairly quickly. And then finally, as we've discussed, these 2D video systems are providing probably the most useful information in the video itself. And so regardless of what data that you're using, from drawing or an IMU sensor or anything, the video data itself is always going to be usable. Now let's jump to the other side here and look at 3-dimensional systems. So the benefits here, first and foremost, are going to be precision. Particularly with your optoelectronic systems that you have seen to be validated through many, many research articles. And also those systems have the ability to capture movement with a accuracy, in the sub-millimeter range. Even some of the other systems that we mentioned, the IMU and the markerless motion capture systems, also aid in this precision. With the IMU systems able to capture orientations and rotations within 1 to 2 degrees in most cases, and the markerless systems also able to capture movement within a known volume similar to that of the optoelectronic systems. But that precision is really what's going to set these systems apart from the 2D systems. Also, adding depth. So that third axis, being able to capture rotational components as opposed to just looking at the up and down and side to side movement that you may see from a video. Of course, a benefit for a 3D system is the comprehensive data sets that are provided. So not only the precision, and then the third axis that's allowed with the use of a 3-dimensional system, you now have a comprehensive data set that you can start to look into to potentially evaluate somebody's movement patterns and make a more and more informed decision. And then finally, 3D systems tend to be a bit more automatic in their operation. So generally for some of the 3D motion capture systems, the optoelectronic systems, the IMU systems, the markerless systems, they tend to offer the motion analysis data automatically. So you would have access potentially even in real time to looking at the anatomical joint angles or the kinematics so that you can see how somebody is moving and perhaps even use that information as a tool during the rehabilitation process using biofeedback, for instance. Now, if we look at where these circles intersect, we can see that these systems share some benefits as well. So the first one I have listed is portability, and there's an asterisk there. Because while video certainly is portable, you can take it anywhere that you need to and capture people moving however you may need, whether that's, as our discussion today is focused on gait, or even capturing somebody playing a sport, or performing a job, if you're looking at ergonomics, for instance. You've got that ability to take video wherever you need. The 3D systems also offer portability. Probably at the highest or at the top level, you're going to see inertial systems be utilized in these portable contexts. Again, the idea that you do not have to be withheld to a certain volume of space gives you the ability to capture that three-dimensional data in these realistic environments. But these companies that develop the other three-dimensional systems, the markerless and the optoelectronic systems, typically can also be portable as well. There just is a little bit more attention that needs to be paid in terms of calibrating the cameras, setting up the correct environment. And then of course, again, you're still only limited to that certain capture volume. Of course, the benefit between the two, for doing motion analysis, either with video or with the three-dimensional system, is that you're gathering objective data. And you're using that to drive your decision-making process. As we mentioned, the 3D systems may be a bit more comprehensive in the data that they provide, but nevertheless, having data even from a 2D system can aid you in making that decision. Next, with the technology advancements, both in the three-dimensional space and also, of course, per usual in the 2D space, both these systems are going to be unobtrusive to the movements. So the idea is to be able to capture somebody in their most natural place. Be able to see them walking or doing any other activity without affecting their movement because of the devices or the technology that's being utilized. The marker sets that are used for the optoelectronic systems are generally small markers that don't weigh too much, and so you can't feel them usually. Of course, the markerless systems, they don't require any instrumentation. And then even the inertial systems, while you do have sensors on you, again, they are also light and typically low in numbers, so they're generally unnoticeable by the subject that you might be measuring. And finally, all this information is enhancing. So it's making your observational gait analysis or whatever observational motion analysis that you might be doing better. As we discussed, having access to that data is going to allow you to make a more informed decision or potentially validate what your decision tree might already be showing. Now let's move on to the limitations. So again, we'll start with the 2D system. Primarily, the biggest issue when capturing or performing analysis with a two-dimensional video system is a phenomenon known as parallax error. And what that shows, and we'll go into this in detail here in just a moment, but essentially with different angles of view, you're going to have different measurements. And that is a limitation of only being able to capture information in those two planes. Next is going to be manual analysis. So generally with a two-dimensional system, you have to either draw on these video frames. Even if there are markers to track, there's usually some form of manual editing that is required either at the beginning of the measurement or at some point within. So there isn't that automatic data to be provided the same way that it can be with a three-dimensional system. And then finally, there's no transverse information. So as we've discussed, you don't have that third plane. And capturing the rotational information is going to be paramount if you really want to go into detail about how somebody is moving. Looking at the three-dimensional systems, their biggest limitations are usually one, that they're fairly costly. They come with a higher price tag than a two-dimensional system. And that's because there's a lot of technology and development that's been put into these systems to provide this level of objective data. Over years and years and years, engineers have focused on using this information and taking the techniques drawn from physics to be able to capture movement and provide this information at a very high level. And so, of course, with that comes a price tag. Next limitation, which we also mentioned as a benefit, is that it's data rich. This can, in certain cases, depending on who you are, be a limitation because you may suffer from the paralysis by analysis phenomenon. There may be so much data looking in all three planes of movement that you potentially start to identify or pick out things as issues that may or may not actually be an issue. So while on one hand, it's a benefit to have access to more data, on the other hand, it could certainly be an issue, but that's going to be dependent on the operator. Can you have a particular question set up and use the information that you're gathering to answer that question? Next, the 3D systems tend to have more intricate operation than the 2D systems. So these are going to be detailed and nuanced operations, with regards to calibration or however you might be setting the system up. Perhaps some details about where markers are positioned or sensors are placed on the body. And so this usually requires a certain level of individual to operate the system, or just a little bit more of a steeper learning curve when you begin to adopt this technology. Now, if we look at the intersection here, we've got a couple limitations that these systems share. First is going to be occlusion. And we'll get into this into detail here in just a moment as well. But really, this is a limitation experienced only by marker tracking with 2D video and marker tracking with 3D optoelectronic systems. The inertial measurement systems and the markerless systems do not suffer from this same limitation. However, all of these systems certainly suffer from soft tissue artifacts. And what I mean by that is that with either two-dimensional video or three-dimensional motion capture, we're trying to model or measure how the skeletal system is moving. But we're doing so by looking on top of all of this soft tissue, whether it's muscular tissue or adipose tissue or both. And when that tissue moves, we register that as data. And so these soft tissue artifacts are probably one of the largest limitations of any motion capture system, and something that should certainly be looked into with a great level of critical thinking. Of course, as technologies and software continues to enhance, we're creating better ways to deal with this, but again, we're modeling bones over top tissue, so that's always going to be there. And then finally, we have Hawthorne effects. And what this provides us is an issue where the subject may perform differently knowing that they're being observed. And this is essentially a psychological effect of any sort of research study. It's normal in any type of capture, whether that's a survey or something sophisticated like what we're talking about today. So let's jump into one of the limitations that we had mentioned, which is parallax error. And so this is, again, showing that with different angles, we have different measurements. And you can see here in this great picture that I pulled from drivelinebaseball.com that we have a 90-degree angle shown with the camera facing directly perpendicular to the object. But if we just alter that angle of where the camera is viewing, it now shows a completely different measurement. This has to be understood when utilizing two-dimensional video analysis. It is absolutely important to position those cameras such that you are facing the perpendicular aspects of the subject that you're capturing. They need to be completely 90 degrees in orientation from the subject. If not, then the reliability of your data is compromised. So again, if the video is not taken exactly from the same position, and more specifically the same angle and same distance, then your measurements are going to have a large margin of error. Another limitation that we discussed was marker occlusion. This can be shown here, where this individual's arm crosses over where we would have a reflective marker shown in the video. Depending on the technology that you're using, again, there's been some developments in software to help deal with this, but generally, if there's missing markers, then there's missing data. And that's going to cause some potential issues because the inconsistent tracking now requires help from some sort of estimation techniques. And while the development of those estimation techniques has been certainly enhanced and can be looked at for most applications, there's always going to be the chance that you're now relying on estimated data as opposed to truly measured data. Again, the interesting thing about this is that it's unique to the 2D video analysis systems and the 3D optoelectronic systems. Inertial measurement systems and even markerless systems do not suffer from this because they're not tracking these markers in that space. So something to think about. Now, if we move into what the research has to say, there's a couple quotes that I pulled out here. First and foremost, I'd like to note that there's several studies, and this is, looking at the Google Scholar citations, over 1,500 that are demonstrating the validity of using two-dimensional video as it compares to a three-dimensional system. So you may see there at the bottom that the kinematic approaches will adequately represent sagittal plane motion, but they may be insufficient for describing ankle and planar and dorsiflexion. Additionally, as we discussed, there are not options for capturing the transverse plane. Another thing to mention is that interpretation of 2D video analysis should be absolutely critical. Because of that setup, the issues with parallax error, possible marker occlusions, even inter and intra operator reliability issues, you can see that there's some extreme variability that can be determined. As mentioned in the quote there, 3 to 8 degrees and 9 to 14 degrees in certain aspects. Of course, an 8-degree error is going to completely change your evaluation of an individual's movement pattern. So again, just harking on the importance of setting up your system in the appropriate way. Now, if we move into three-dimensional analysis, there are several more studies that have been cited, roughly 35,000 plus, and probably even more than that. And as I mentioned, these are the, in the case of optoelectronic systems, the gold standard operation of motion analysis. And the three-dimensional data shown from inertial systems as well as the markerless systems have been demonstrated to be reliable as well in comparison. But the idea here is that it's able to be reliable and can accurately measure those three-dimensional kinematics. So looking at all three planes of motion. One limitation going back, and this is the quote up in the top right here, is that this average gait lab with maybe a traditional setup, EMG, force plates, and optical motion capture system generally requires a lot of manpower, a lot of labor, a lot of time spent not only setting up and capturing data, but then analyzing that data. Typically, this comes with an increased expense. And so this is something that most clinics may not even be able to afford just because of that particular time cost. Certainly with, again, the advent of inertial systems or the markerless systems, there are some of that time has been reduced. Even with the optical electronic systems and the softwares that they've put together, that's being reduced as well, probably significantly since that article was written. But I think in general, just demonstrating the details and the necessity for capturing this information, it does require a lot of manpower to really drive the full potential of these systems. One quote that I found that I think is really interesting, especially when looking at the comparison of these two types of devices, is that we need to be mindful of the limitations of gait analysis in general. Patients are usually already injured. There's differences between walking on a treadmill versus walking over ground. The Hawthorne effects that we discussed earlier, the observer expectancy effects and the subject expectancy effects. But we need to be mindful of these limitations and understand that they apply equally to both of these approaches. So regardless of what system you ultimately decide to move forward with or use in your space, you have to approach it with a critical mind and take the data for what it is, a tool. These systems, these measurement systems, are not going to provide diagnoses for you. They're not going to make decisions for you, but they're just providing you with more information to add to your tool set, your repertoire, to be able to drive that clinical decision and make perhaps a more informed decision. Now, let's take a look at a couple examples here. I know we've got roughly 10 minutes, and I do want to have some opportunity for questions. But if we look at an example of an individual walking, we can see that we're just capturing these sagittal plane kinematics. We've got the markers that are being tracked. What that provides to us is hip flexion, knee flexion, ankle dorsiflexion. Sometimes we can often even capture trunk lean with a marker set up this way. But that's often one that suffers greatly from that parallax error because we tend to rotate while we walk. And so the rotation of this shoulder marker may actually induce some false positives of trunk lean. But generally, I mean, this type of information, this analysis is certainly enough for somebody to look at and try to understand. I think, aside from some of the issues that we already presented, the only other thing is that you're just limited to capturing one side. So, maybe this is the injured side. but then you have to reset up the entire thing or let the individual flip around and walk the other direction on the treadmill to capture the other side. But those are two separate recordings. So now you've got two files that you need to merge and somehow compare. Certainly there's ways that we make that easier, but you know, in general, you're limited. Now, if we take a look at a three-dimensional analysis, we now have a rendering of this body model. We can see the depth. We can look at the rotational components, which are generated from this, this data that you see here. So not only do we have the sagittal plane, but then we've got the frontal plane and the transverse plane information. We have them overlaid in these cases and being able to see the relationships between these movements. Those can be captured for not only these joints, but then perhaps, you know, even the ankle or the knee, or, you know, if we were to extend up into the trunk or the rest of the body. But we've just got more information to start to look at. So we can see within this three-dimensional analysis, are there leakages? Do the strategies or the patterns that we see, do we start to see them bleed into other areas? You know, is rotation or range of motion limited in that sagittal plane? And if so, is it because there's extra rotation or range of motion in one of the other planes? That's not possible to even try to investigate or evaluate with a 2D system. Now finally, if we look at these compared to one another, and I've just pulled out the sagittal plane angles, but you can see how they differ. So the pink is going to be generated from our three-dimensional system, which is an inertial motion capture system. And the blue is generated from our marker tracking in the 2D video. Look and see how the differences between the data exist. The blue system tends to be a little bit underestimated in certain spaces, a little bit overestimated in certain cases as well. Generally, the patterns are the same. I think that's a plus, right? Looking at the sort of relationships between these two and seeing that, okay, the general movement patterns are there. But when it comes down to looking at this as objective data and utilizing it, you want to be sure that what you're capturing is accurate, an accurate representation of that individual's movement. One thing to note in particular, and this is one that I'll pause at, but right here. So this gentleman is now in mid stance, and we have roughly a 10-degree difference in knee flexion. And that is completely due to that parallax error that we had mentioned. With the 3D system, we're able to accurately capture the rotations of these body segments, regardless of whether there's rotation present or not. In the 2D system, however, there's some slight additional knee bend, mostly due because of this individual's internal hip rotation. And so that's causing this slight bend of the knee that is actually not present whatsoever. So something interesting to look into. Now, I'm going to skip through this next slide, which kind of breaks down some of the gait phases here and kind of shows a report of this information. We'll go through it a bit quicker than I had anticipated, but I do want to leave some time for questions here. So these are the gait phases, and you know, within this system, the Noraxon system, we're able to generate gait reports. And so I was able to do that for to do a comparison of each one of these phases and look at the differences between the data represented by the 3D system and then the 2D system. Again, I think something to note is the general plus or minus 5-degree difference between the video tracked information and then the measured information from the sensors. So as we step through here, you can see that pretty much consistently throughout. Again, the 3D system also offers us additional information to where we can look at the frontal plane and the transverse plane information and not only be limited to this single plane with the video. So with the IMU system, we have access to more data. There is the difference there that you're noticing with the plus or minus 5 degrees of variability, but that doesn't mean that this system is still not useful. You can still operate with it, but it just depends. So it brings me to the conclusion here. Which one is right for you? And I think that all depends on your priorities. Some of the initial points here would be related to your budget and your time. How much time do you want to spend? How much money do you have available to utilize a new technology? Or are you looking to have more comprehensive analysis and you want access to that rotational data? Taking these considerations into account and some of the information that I presented to you today, hopefully that gives you with a little bit more ammo to approach this decision and understand, what is best for you. Making that choice based off of what your needs are and not necessarily because you may be worried about, not having the highest level of technology, but, you can still trust information. And again, even with video in general, at the end of the day, that's going to be always usable. So take that into consideration. And of course, at Noraxon, we do offer a multi-device setup. And so you can reach out to us and we can have a further discussion about some of these systems and how they integrate within our platform, not only for the motion capture side of things with the inertial measurement and the video, but then looking at neuromuscular activation patterns, looking at kinetics through force plates or pressure instrumented modalities, even the integration of some analog signals such as isometric dynamometers. In any case, we're here to answer your questions and we want to consult with you to provide that best process going forward. We want you to be successful in whatever it is that you are looking to measure.